can hear me clearly? Is everyone hearing me clearly?
Yeah.
Okay, I want to welcome you to my lecture today. Of course, we're meeting remotely today because of the little emergency that I have. And of course, it's already clearing out. I'm going to return to in-person teaching on Wednesday. Okay, so I want to welcome you to my lecture today. Of course, today we actually gonna start a new topic that we call matrix factorization in machine learning. Okay, so I need you to pay attention because this is very, very crucial in machine learning and statistical world in general. Okay, so in the outline. I'm going to walk you through some fundamental principle of material matrix factorization. Of course, I'm going to walk you through some technique of matrix factorization, that include the principal component analysis as a factorization technique, the singular value decomposition, the AU factorization, the Cholesky decomposition, the QR factorization, and I'm also going to talk about non-negative matrix factorization. So all what I need from you is just to sit back and, ask question where necessary in case you actually need some kind of clarification. Okay, so before moving forward, I want to confirm again if you're all hearing me clearly. So is everyone hearing me clearly?
Yep.
Okay. Okay, so I'm actually gonna be asking that question from time to time in case if there's anyone who is not hearing me clearly. Okay. Give me 1 second. I think I'm gonna do this now. Having, don't know why it's not letting me to, let me do this. Okay, I think it's working out. Okay, so I want to start with the matrix factorization. Um, like I said, in case you need a clarification, you can ask me a question. I want this to be like a normal in-person class. Okay, so let me first tell you what do we understand by matrix factorization. Okay, so by matrix factorization, what we actually mean is it's a mathematical way of decomposing or splitting, a matrix into two or more simpler matrices. I'm going to say that again. You know, we normally work with a complicated data, right? We actually have large data set. Okay, so what the matrix factorization is just going to do is a way to have what I call efficient decomposition, okay, of our large data set, okay, into smaller parts. Okay, so and that was why I said, if I have a matrix, okay, and we now split it or we decompose that into two or more pieces, and those pieces are also matrices on their own, in such a way that when we multiply the pieces together, okay, it's approximately going to give us the original matrix. Okay, so that is what we mean by matrix factorization. Now, let me tell you this. Do you know that the principal component analysis that we've done before, okay, is also one of the matrix, it involves matrix factorization, okay, and I'm actually going to explain that to you. you remember the other time, when we apply principal component analysis. Of course, we apply principal component analysis because we realize we got a dimensional data set and we want to reduce the dimensionality in the data set. Okay, so reducing the dimensionality in the data set, okay, and what we that will involve splitting our matrix into two or more simpler form. And of course you actually what we normally split when we talk about your principal component analysis, we normally split you know, the covariance matrix, okay? You split the covariance matrix, and of course, you're actually going to get the Eigen decomposition. Okay, you're going to get, remember, we get eigenvalues, we get eigenvectors, okay? So I want to tell you the principal component is an example of matrix factorization, okay? Because we're able to split, the covariance matrix into some matrices that involve the diagonal matrix. The diagonal matrix is one of the pieces. The diagonal matrix are actually going to have the eigenvalues. Don't forget, the eigenvalues are going to be the variance of each of the principal components. And of course, we're also going to have another matrix that we call eigenvector. Okay, the eigenvector. So don't forget, they're actually going to be the loadings. Okay, so this is just to confirm to you that principal component analysis is one of the matrix factorization technique. And not only that, another very important factorization, matrix factorization technique is what we call singular value decomposition. But before I go into singular value decomposition, I think I want to show you algebraically, okay, how Eigen decomposition work. Okay, take a look at what I have right now. If this guy is a matrix, okay, which could be a covariance matrix, okay, in the principal component analysis, we're actually going to break it down into these three. You can see we got three set of matrices now, okay? So, and of course, you know what the first one, the U here, what the U stand for? So the U here is actually what I call the eigenvector of A transpose, okay, which is what I'm talking about here, okay? And of course, this guy here is the diagonal, matrix, okay, which will contain the eigenvalues, and of course, this guy here, also the transpose of that is just talking about this. Okay, so now this is the Eigen decomposition. So just to tell you that, okay, the principal component is also a matrix factorization. Okay, now going into another one now that we call singular value decomposition. So the singular value decomposition is another decomposition of matrix A. Some of you may be wondering, okay, what do we use the principal component analysis for? What do we use the singular value decomposition for? Okay, we actually use two of them for dimensionality reduction. I'm going to say that again. Okay, the principal component analysis, the singular value decomposition, we use them for dimensionality reduction, particularly the two of them has application in face recognition and image compression. Okay, the two of them. Okay, so they are very, very important in compressing data. And I told you the other time, the reason why we want to compress our image is because of the fact that we do not have unlimited data storage. And that's why at times we may actually want to have a way to reduce the numbers of pixels in image. And the way to do that, we can go by principal component analysis. which involve the gene decomposition. And we can also go by way of a singular value decomposition. Okay, so I'm actually going to tell you the difference between the two. So the way the singular value decomposition work, we're actually going to work with low rank, approximation. Okay, when we start with original dimension of the matrix, okay, we actually, because the original dimension of the matrix, the rank, when the full rank, the rank of the original matrix is actually going to have complete perfect information. But you know what? We don't want a complete perfect information because of the storage. And is there a way we can actually eliminate, some features? Okay. And, the single value decomposition, we actually be seeking for a lower rank. Okay. A lower rank. A lower rank means I'm actually going to lose some kind of information. Okay. But you know what? I'm still going to retain the quality of my image. Okay, so you're gonna see the difference between the two, by the time I use some example. Okay, now I want to talk about singular value decomposition because you understand the principal component analysis. I said the two of them, they are very useful in dimensionality or reduction, of course, in class. I've already walked you through the principle behind principal component analysis, but what I want to do right now is to walk you through the principle behind singular value decomposition. But before moving forward, can you confirm again if you are still hearing me clearly? Is everyone still hearing me clearly?
Yeah. Yes, sir.
Okay, thank you so much. Okay, so like I said, we are under SVD now, that we call singular value decomposition. And I said this actually help us to represent a large image matrix. Like here now, take a look at this guy now. Okay, this matrix A. Okay, it's actually we're gonna refer to that as an image. Of course, we all know our image is dimensional. Okay, so how do we now represent that in a reduced form? Okay, by ignoring, what I call the less important singular values. So what we're going to do, the reason why we call this a singular value is because there's going to be a lot of singular values. Okay, the number of singular values will actually be equal to the rank of a matrix. Okay, I'm going to say that again. The number of singular matrices, okay, this number of singular values, okay, it's actually going to be the numbers of, going to correspond to the numbers of rank. Now, let's say if a full rank of the matrix is 10, I'm just assuming, it means it has the total numbers of singular values is going to be 10. But you know what? We don't want to use the old 10. Can we have a way to use value less than 10, even though we're actually going to lose some information, but you know what? The quality of the image is still going to be preserved. So I'm actually assuming we got a matrix A, okay, which is n by n, and we're actually going to split that into what you're seeing right now. Take a look at that. We're splitting that into three smaller pieces. Okay, U, D, and the transpose of V. Take a look at that. Okay, we can also write that out in a scalar form to be this. Okay, you can see that. Okay, so the sigma, when you take a look at D, okay, the other very D, is the diagonal, matrix for the singular values. And the singular values, in the diagonal, you actually are going to have sigma 1 greater than sigma 2, greater than sigma 3, and so on like that. You're actually going to have that in there, descending order, where the first one is going to be the largest standard or sigma 1. Okay, so when you have it that way now, okay, so what we actually want to do is let's say for instance I want to use this in image processing now. If I want to use this in image compression now, Okay, what I'm actually going to be seeking for is I don't want to use all the singular values. Because if I use all the singular values, I am going to have the complete image, the perfect information, but we don't have resources to store or, to store that. And that's why we're actually seeking for lower rank approximation in such a way that what we're going to end up with at the end of the day, is still going to retain the quality of the picture. Okay. Now, so that's what we mean. That's the idea of a single value decomposition. Okay. Now, like I said, we're still going to have a way to maintain the image quality, even though we're gonna lose some information. Okay. So, I said something the other time. Okay. I said something the other time. I said, you know, we are seeking for low rank. Okay, don't forget the rank we're seeking for is actually going to be lower down the dimension, okay, of the matrix, okay, because if A has a full rank, okay, we say that R is going to be the minimum of that, okay, if K has a full rank. But what we're actually trying to do, we want a lower rank, okay, which means we don't want it all the single values, okay. We only want to use the top number of the single values, okay. And at the end of the day, even though we're still going to have we're going to lose information, but the benefit is we're able to retain the quality of the image, and not only that, we're gonna save memory or disk space. Okay, so that is the intention here. Okay, now I understand that one. Now I'm actually gonna move to the next slide. Now, in this next slide, oh my God, because don't forget, we actually, if I take you back here, okay, if I take you back here, you can see right now that we decompose A into these three smaller pieces or smaller matrices. If you take a look at this now, if I multiply all these pieces back, okay, I'm actually gonna get something equal to that or approximately equal to that. Okay, because it is not all the time that we're going to get the exactly what I'm going to say. When you factorize your original matrix into two or more matrices, by the time you multiply the pieces together, you're actually going to have whether exactly original one or approximately. And because of the word, approximately, of course, we're actually going to be seeking for optimization problem. Okay, we are if you take a look at this guy and this guy now, so maybe this is the original matrix and this is what they are after multiplying the pieces of the matrices that was broken down into, we actually want to minimize the sum of square distance. And this is going to involve, this is going to be an optimization problem. Okay, so right now we're actually minimizing that, okay, the sum of squared, okay, and we're minimizing that around M. Okay, so like I said, yeah, if you take a look at what I have here, I said when we compress a matrix A, which might be a full rank matrix, like having maybe an image, the original image right now, to a certain rank value. Of course, we hope to retain as much as information as possible. We know we're going to lose some information, but we want to still retain some information that will not affect the quality of the picture. And I said, natural question is, okay, what is the best low rank approximation to the original matrix A? Because let me tell you, if a matrix has, let's say, for instance, the original picture, maybe the rank is 896. I'm just assuming. Okay, now we want to go lower than 896, and the question is, well, we don't want to go to the lowest, because we're actually going to lose the image totally. The image is going to be blurry. So, so the question now is, what is going to be allowable lowest rank that is going to be before we can see say that okay, the image still retains some quality. Okay, and that's why you see subject to rank m less or equal to q here. So because we actually given the rank q, we want to reduce it to something. Okay, now I want you to pay attention before moving forward. Okay, I want to ask this question once again. Is everyone still hearing me clearly? Is everyone still hearing me clearly?
Yep.
Thank you so much. Thank you for confirming that. Like I said, I'm actually going to be asking this question from time to time. Okay, now I need you to take a look at this image. I want to use this image as an example right now. Now we want to compress a grayscale image of William Cochran. Okay, get your calls and Harold Otterlin. These are, very renowned statisticians of our time. Now, if you take a look at the first picture here, okay, now let me first tell you this. The original rank of the full image is 886. You can see this is the original rank, right? This is, you can see everybody clearly here, right? But we got a problem of storage because, we don't have it, a limited storage facility to store, or don't forget, each of the dimension here has a pisu in them, okay? So what are we going to do? If you take a look at the first one here, if it's okay, so which means here, when the rank equal to 886, the number of singular values will be 886. I'm going to say that again. Don't forget, the number of singular values equal to the numbers of rank of the matrix. Now, if I say, okay, let me use 10 rank, if you take a look at this guy now, what do you see? The image appears blurry because or only a small portion of the information, okay, is used to approximate the image. That's why it's blurring. Okay, can you see that? Now, when we use a rank of 20, okay, now it means we've actually used top 20. We've used our top 20 singular values. Okay, don't forget I said the singular values that I showed you the other time going to have sigma 1 greater than sigma 2 greater than sigma 3. So here we've used the top 20. And we take a look at this one now, where we use the top 20. This is less blurry compared to this, okay? Because more details are visible, but still lack sharpness. If you take a look at this now, it still like sharpness. When we increase that to 40 now, okay, we use that to 40, we get the rank for the approximation now, provide even more clarity. Can you see more clarity right now compared to the A and B? Okay, now individual faces and other details in the image are becoming more recognizable when you take a look at this. When I increase it to 80, okay, when we increase that to 80 now, what do you see? You can see the image look quite close to the original, and many details are visible. Okay, many details are visible right now. And of course, the only thing that is missing right now in the rank equal to 80, okay, the only thing that is missing are, are just some details, okay, and those details, so from what I'm saying now, the image is nearly fully reconstructed, okay? Now, is there anyone who need clarification on this? I'm explaining singular value decomposition as it applies to image reconstruction, image processing, image compression right now. Okay, now I'm actually going to move right now. I want to move to other fit or matrix factorization that we call LU. Now, let me tell you this. When you talk about LU factorization, okay, it's not directly involved in face recognition, applied into face recognition or applied to image processing. Not that is not a direct algorithm for that. Okay, so this guy is only used in solving system of linear equations. So the LU factorization is just to split, a matrix A into L and U. Where, L is actually going to be a lower triangular matrix and U is going to be upper triangular matrix. So, this idea is actually used in solving system of linear equations, also a matrix inversion, you want to find the inverse of a matrix, stuff like that. Okay, so LU factorization is highly applicable in mathematical field. Okay, and in statistics in general, where you want to find the inverse of a matrix or you want to solve a system of linear equation, and that cut across scientific field from electrical circuits and so on like that. Now, another technique under matrix factorization is actually called Cholesky decomposition. Okay, so when you talk about Cholesky decomposition, actually decompose a positive definite matrix into a product of a lower triangular matrix and it conjugate transpose. If you take a look at this guy now, okay, this is like having L and the transpose of L. So this is also very useful, okay? In fitting linear regression, the generalized linear model, the Kalman filtering for signal processing, Gaussian directed graphical models, are also very useful in facial recognition, okay? But the issue with this is that, using using Cholesky decomposition or the LU factorization, all of that. Okay, uh, they are very useful in decomposing matrices as a step in a larger algorithm. Okay, they can be used as a step in larger algorithm, maybe larger algorithm like principal component analysis, or you want to talk about the singular value decomposition and so on, like that. But they also have their uses. Okay, they got their special uses. Okay, so I wanted to take note of all of that. Okay, so I'm going to say in summary. Okay, I'm actually going to say in summary, the same thing also applicable with QR factorization. That we factorize matrix A into the product of an orthogonal matrix Q, an upper triangular matrix R. So that's also very useful in solving linear system, in linear regression, in eigenvalue computation, in Gram, Smith orthogonalization. Those are very, very useful technique as well. I want to ask question again. Is everyone still hearing me clearly?
Yes, sir.
Okay, thank you so much. Thank you for confirming all of that. Okay, I want to go into another important, I need you to pay attention now. Non-negative matrix factorization is very, very important when it comes to machine learning world. Why do we call it non-negative is because we want to make sure that the matrices that this is broken down into, they are also non-negative. And why do they need to be non-negative? They need to be non-negative because with non-negativity, they're going to be more interpretable. I'm going to say that again. Okay, they're going to be more interpretable when we ensure that the lower matrices that we split an original matrix into, so if we ensure that non-negativity, of course, it's actually going to make it to be more interpretable. Okay, I just wanted to understand that. But the issue with this is that it is not going to give exact factorization. It's going to give approximate. What do I mean by that? It means that, okay, when I you know decompose a matrix into two non-negative matrices, by the time I want to multiply the pieces together, it's not going to give me the exact original matrix. That's what I mean. It's always going to give the approximate one. That is exactly what I mean. Okay, so I'm actually gonna walk you through that now. I need you to pay attention now. It's like we are having the original matrix. Okay, as you can see right here, the original matrix is X, and that very X is actually P by N. Of course, the way we normally have our data set, right? The way we normally have our data set is going to be in a matrix form. Okay, so when you have it in a matrix form, you collected the data across the number of observation and features. Okay, I want to believe you still remember the way the multivariate data set actually used to look like. Okay, so what I'm trying to talk about right now, okay, looking into this particular, this guy is a matrix, original matrix X, and the dimension is P by N, okay, and you know what, we want to have a factorization in such a way that we actually want to have, don't forget, we're seeking for lower rank, okay, which is going to be much more less than the minimum of that. And you know what? We're going to partition, we're going to decompose the original matrix X into W and H. I'm going to say that again. We're going to partition X into W and H. And let me tell you the way it's going to look like if I want to write it out. Okay, the way it's going to look like, I'm actually going to be having X. I'm not going to say equal to, I'm going to say, approximately equal to, I'm going to say W, okay, then, and H, okay? Now, if you take a look at what I have right now, okay, the W is actually going to be P by R, and your H is going to be R by N. And let me tell you this, because of the fact that this is not, X is not approximately equal to this, we expect to have a gap. So if you take a look at this guy now, this is a distance matrix, okay, which is going to be the distance between, the original matrix X and the product of the of the pieces. And of course, we actually want to minimize this guy right now, and that's why you say the sum of squared of the original matrix, okay, minus the product of the split, okay. And you know what? And we're also going to impose the fact that we want our the W matrix and the H matrix to be non-negative. Okay, we actually want it to be non-negative. Okay, so, and I told you the other time, the non-negative is actually to make sure that it's interpretable. Okay, so now this is how this is a mathematics around the formulation of the non-negative matrix factorization. Okay, so when you take a look at what I have right now, okay, I'm going to walk you through this example right now. Okay, we actually, because non-negative factorization as application when you talk about documents, in document models, in image processing, in face recognition, and so on. What I want to do right now, I actually want to believe that what I have right now, this particular diagram that you're actually seeing right now represent the non-negative matrix factorization, okay, applied to text data. Okay, we want to apply this to text data now, okay, which we normally use in topic modeling and document clustering. And what is our goal here? Our goal is actually to use the non-negative factorization to approximate a given matrix X. Okay, and that given matrix X, don't forget, is actually going to be the product of two smaller non-negative matrices. Don't forget, two smaller non-negative. Don't forget what I told this W and H. These are the non-negative that we talk about. This is the original X. Now I'm gonna walk you through the breakdown right now. If I have the original matrix, oh my God, when you have the original matrix is actually gonna be called a document term matrix, where in each row you're gonna have document, in each column you're actually gonna have words. Okay, so now it's gonna be document by words. Okay, now. And don't forget, the entries in the matrix will indicate the frequency or the weight of word in each document. You're going to have what is the number of word in this particular document. Now, when you take a look at the dictionary now, oh my God, when you take a look at the dictionary now, that actually represents a set of words, okay, that occur across all documents. Okay, a set of words that occur across all documents. Okay, I wanted to take note of that. Now that has been broken down, okay, this guy here is actually the W. Okay, so what do we mean, by the W right now, that this guy is being broken down into, okay, I'm actually gonna explain that. And I'm actually gonna explain this particular guy. Now, if you take a look at the W here, okay, the W here actually represents some keywords. Okay, the keywords or group or topic that frequently co-occur in the documents. Okay, we don't want to use all the words. This is like what you see here is going to be like the feature that you extract, the important features that you extract. That is what it means. Okay, I'm actually going to say that again. The W, so what you say, the first one here, the W actually represent keywords. Okay, some keywords, some important words, the group of words or topics, some key topics. That's exactly what it means. And these guys here, okay, actually show also, the extent to which this topic are present in each document. That's why we call it the weight. Okay, this is the weight. So in case you want to reconstruct the set of the dictionary, okay, you're going to use this to multiply that. But don't forget, at the end of the day, you're only going to get the approximate. Okay, so this is very useful in topic modeling. Okay, now I think I've just explained that the document is a mixture of multiple topics, and each topic is associated with word of different weights. Okay, I think I just mentioned that. Okay, so I want us to apply that in image feature extraction now. Okay, now but before moving forward, I want to first confirm, is everyone still hearing me clearly?
Yep.
Okay, thank you so much. Now, right now, okay, I got the original X, and that is being decomposed into this and that. Okay, don't forget we are decomposing into W and H. Okay, now our X is actually going to be the image data matrix, the original one, and don't forget, X represents what I call the matrix of facial images. If you take a look at this guy is for this particular image, that guy for that particular. We got a lot of images, of course, get a lot of images. So this guy is the original matrix S, okay, that actually, where each column correspond to a different face. Okay, you can see different face, right? Each column. Then each row, okay, correspond to the pixel values. Pixel value, okay, from the face or facial images. So each face we have their pixel value. That's why there is a matrix. So if I want to decompose right now, I'm actually decomposing to W. okay? And I'm decomposing to W and H, and I'm going to tell you, what the W actually means, okay? The W here, okay, this guy now, the rectangular matrix, okay, to the left of the approximation now represent the basis vectors. When I talk about the basis vectors, I'm actually mean some important features in the face, like eyes, nose, or mouth. Okay, that is what this guy actually mean. Okay, now when we talk about the other side, the weights, okay, that actually represent the coefficient or the weight for reconstructing each face. Okay, so using the feature in W. Okay, and don't forget, I told you that at the end of the day, you're going to have the approximate one. Okay, so that is exactly what I just talked about. Now, as you can see what I talk about. Like this one is the extracted features, important features. Okay, like face. You can see face here, like nose, and so on like that. Okay, no, it's not going to be the all features, the significant one. Okay, that's what you mean. Now, do you not know what I want to do here now? What I want to do here now is to compare the NMF is non-negative factorization with the principal component analysis in, application to image feature extraction. Okay, now, and I need you to pay attention now. So how can we actually compare both principal components analysis and the non-negative factorization, for this, okay? And because of that, I needed to pay attention right now. Now, let me start with this guy, okay? This is the original, if this guy is the original face, we can see, if I start with the original face, okay, NMM is going to partition that into two, but don't forget, this is going to be non-negative, non-negative, okay? But in the principal component analysis, okay, you can't guarantee non-negativity, okay? I just wanted to take note of that. So when you take a look at the left grid here, like I said, okay, this particular, oh, sorry, take a look at this particular one. This is the original matrix. And as you can see in the original, that actually break down into, you can see the eyes, or you can see the nose, you can see the mouth. And you know what? The NMF forces the non-negativity in the components will mean that the pixel value can only be positive or zero. That would make sense. Okay. The pixel value can only be negative or zero, and that will make it more interpretable. Okay. I just wanted to take note of that. Okay, so the middle here, if you take a look at this guy, that represents the weights that are multiplied. Okay, I just wanted to take note of that. And of course, when you take a look at this, that is the W that I talk about. Now, in the principal component analysis, this is the original one. Okay, as you can see. And of course, if you take a look at this guy, that shows the principal component extracted. Okay, the principal component extracted using the PCA. Of course, we normally extract features as well. Okay, and of course, weights, the loadings. Okay, so this is just to show you how we compare the two. Okay, but I wanted to get a key point. Okay, what is the conclusion we're going to have from this? The conclusion we're going to have from this is that the NMF is better for learning distinct and interpretable part of the data, while PCA is more effective in capturing overall variance. I wanted to take note of that. NMF does not capture overall variance, so the two of them are missing something. NMF is more interpretable than PCA, but PCA capture the largest variation. And that is the reason, so the both method can actually be used to reconstruct image, but the underlying components are different. They have different characteristics. If you want more interpretable, if you're focusing on interpretability, then you should use non or negative matrix factorization. But if your focus is more on the largest variance, the largest contribution, the largest, don't forget the PCA is about variance maximization, then you go for PCA. Okay, now how do I calculate the NMF? Okay, I told you the other time in NMF, we actually want to minimize the sum of square distance between the original matrix and the two components that was splitted into, and we also want to minimize, want to make sure that W and H are non-negative. This is going to be a non-convex, and of course, a non-convex will not guarantee a global optimal solution. And it's going to be NP-hard. NP-hard means non-deterministic, polynomial time. Okay, so it could take forever. Okay, and you know what? We're going to consider biconvex, because we got two variables that we're minimizing with respect to. We're actually going to do that one at a time. We're going to fix W, with the objective function we're going to be with respect to H, then we fix H, and the objective will be with respect to W. Then, and then now, until we actually have a convergence. Okay, that's what we do. And that's what I'm trying to explain right here. Okay, you have a 20 algorithm for NMF. We just want to introduce one of the most natural algorithms for such a biconvex problem, because it's going to be a biconvex problem, alternating minimization, a special case of coordinate descent. So don't forget, any optimization process is actually going to start from initializations, right? Then we keep applying the following update. Don't forget, we're going to fix one. We're going to fix a W at its current value. Then you solve for minimizing H. You're also going to fix H at its current value, solve for minimizing W. And each single update will involve solving a non-negative least square problem. And of course, that will guarantee to converge. Okay? Then at the end of the day, you can find the local optima. You may not be able to find global optima because of the non-convexity involved. Okay, so this is how to calculate the NMF. You know what this guy is trying to say. Okay, so calculating the NMF right now. Okay, don't forget, I said the process is going to start with some initial values, and for the matrices W and H, and don't forget they are non-negative, and they can be chosen randomly. Okay, so then what we're going to do is we're going to start, H is updated. If you take a look at this one, say, okay, H is updated by subtracting the gradient. This is the gradient from the H. Look at that. So this guy gamma here is actually going to be talking about the rates. Okay, there are times we choose randomly. Okay, so you remember in an iterative process that we normally talk about iteration rates. Okay, so we do this. The plus here is just saying that we have to make sure that it's going to be non-negative, and we're going to do the same to the W. The plus here also ensure it has to be non-negative. Okay, so this actually guarantees to find what I call stationary point with the appropriate gamma value. Okay, I wanted to take note of that. Okay, so like I said, that's how that is that. Now we got advantages of NMF. It's more interpretable compared to any other matrix factorization technique, including PCA. So this is more interpretable than PCA. But so I just wanted to take note of that. And this allows sparse representation. I'm going to tell you what sparse means. That's what we're going to do next on Wednesday. Okay, sparsing is okay. I got a lot of variables, and in the principal component analysis, we still retain the original variables. Is there a way we can eliminate some? Okay, the sparse is going to come in. Now, this is actually suited for data set with inherent non-negativity. I told you. Okay, non-negativity, the image data, the text data, the gene expression data, they actually involve non-negativity. And of course, the variants of that exists, can be adapted. Now, what is the potential disadvantages? You know, the number one is that it can be computationally intensive, particularly for large data set. Okay. It's gonna be, but I want to believe, you know, we're in the computer world. So technology is advancing every day. So I think we're gonna deal with that. Then deciding the rank is not trivial and often require domain knowledge or additional validation technique. You know, when something requires domain knowledge, because of the different in ideology, okay, the results may be kind of sensitive to the choice of your rank. Like I said, no guarantee for unique solution, okay, leading to what I call potential variability in the composition. Because unique solution, don't forget, it's going to be not converse and it could get trapped in local minimum, okay? Then we will have some convergence issues, and not all algorithm guarantee convergence. So, but we keep improving every day. Oh my God, what is next? Okay, so what is next? On Wednesday, I'm going to walk you through what I call past PCA. We've done principal component analysis, but you know what? The reason why principal component analysis is not interpretable is because the principal component analysis is still a linear combination of the whole features. Now, is there a way we can incorporate something like a regularization technique into the principal component structure, or where we could eliminate some features, some old features that are not important? So without, we're going to call that sparse PCA. So that's what I'm going to walk you through on Wednesday. And when you do sparse PCA, of course, it will make our PCA to be interpretable. And of course, on Friday, I'm going to walk you through matrix completion, situation where we got a matrix and we got some values that are missing. So how can we estimate those values? I want to tell you there was competition organized by Netflix, by Amazon, particularly Netflix. There was a time they put an award of $1 million. They were looking for, before they will recommend their movies to audience, to their customers, they actually have some customers to rank the movies. Of course, there are going to be some movies that some customer did not watch, and in that point, that is not going to be ranked, and it's going to be declared missing. And how can we predict them? Because the NECLIF want them to be predicted, okay? And that's why we call that matrix completion. And of course, they started with the mean-square error of 0.9 something, and they needed some people that we reduce the mean-square, the root mean-square error, okay? Because and I think some people were able to do that, and they won the $1 million. Who knows? Maybe you're gonna be your turn. So on Wednesday, I'm going to walk you through sparse PCA. On Friday, it's going to be matrix completion. And of course, I'm going to return to in-person teaching on Wednesday. This is where I'm actually going to stop today. Is there any question before I go today? Okay, so my emergency is already clearing now. I'm actually going to return to in-person on Wednesday. This is being recorded. I'm actually going to share that, okay, at the end of the day. So make sure you all stay safe and have a lovely day. See you on Wednesday. Bye for now, everyone.